A very good afternoon I bid to my fellow panels, Dr. Farah, Dr. Chang, and Dr. JARIAH. I am VASEETHA Ravichandran from 4 BMFG Section 3 Group 1. Would like to present my final year project entitled The Influence of Hydrothermal Aging on the Mechanical Properties of Wood Polymer Composite, or also known as WPC. My supervisor is PM Dr. ZALEHA binti MUSTAFA. So without further ado, let's get started. As a recap from my last presentation, wood polymer composite is classified as one of the sustainable materials which has been utilized for non-structural applications such as decks, floors, chairs, and etc. for a very long time. However, further studies have been conducted by the researchers to utilize WPC in structural applications too, such as in buildings and construction or in automotive industries. This is due to the cause of current worldwide challenges with increasing carbon dioxide outflows and global climate change. Besides that, due to the impact of environment posed by the timber industry, the reapplication of wood and wood-based incorporation with polymer is profoundly encouraged. Moreover, the fabrication of WPC is the incorporation of the waste from the timber industry, and the utilization of the recycled polymer from domestic use is able to provide lower cost compared to the hardwood product. Although the research and advancement in WPC are developing quickly, but this material still requires particular considerations before being received by industries in structural applications because the material's deformation mechanism under short-term and long-term mechanical loading is not continuously identical. Besides that, natural fibers reinforced with polymer composite are susceptible to failure and their mechanical properties differ and break down rapidly in a moist environment compared to a dry environment. Hence, it is essential to study the hygroscopic properties of rubberwood fiber reinforced with recycled polypropylene composite in moist environment and understand their performance changes in static conditions. The study focuses on the influence of moisture on the tensile properties of the rubberwood fiber reinforced with recycled polypropylene composite. The composite is prepared using hot compression molding and consists of a fixed formulation that has been established in previous research. Hydrothermal aging is carried out using water immersion at room temperature for up to 30 days. The composite then was evaluated in terms of changes in weight loss, rate of water absorption, the tensile properties as in tensile strength, tensile modulus, and strain at failure. Lastly, the failure probability of the composite is evaluated using Weibull statistical analysis. The objectives of my project are, first, to evaluate the influence of water immersion on the tensile properties of rubberwood fiber reinforced with recycled polypropylene composite, and to analyze the failure probability of the rubberwood fiber reinforced with recycled polypropylene composite using Weibull statistical analysis. The methodology of my project is as shown in the diagram in this slide. The WPC specimens were prepared using manual hydraulic hot press using an open mold and then cut into the desired dimensions. Then, all the specimens were dried for 1 day at 60 degrees Celsius before the water immersion testing. Water immersion was carried out according to the American standard for testing and material as stated in this slide in a water bath at room temperature. The initial weight and thickness of the dried specimens were measured to a precision of 0.001 gram and 0.01 millimeter respectively before the immersion. For each measurement, the specimens were removed from the water bath, wiped off with tissue paper until the water is gone and immediately weighed. Lastly, the percentage of water absorption rate is calculated using equation 1 where the final weight of specimen minus the initial weight divided by the initial weight and lastly multiplied by 100%. In addition, the water diffusion rate is also calculated using equation 2 where diffusivity is equals to pi times the square of initial thickness times the slope divided by 4 times the equilibrium water uptake. Next up is the tensile test. Tensile test for the samples was performed according to ASTM standard using a crosshead speed of 5 mm per minute. All tests were performed at a room temperature. On a side note, all these tests were done in the previous research and the raw data of this analysis were given to carry out the next step of my project, which is the Weibull statistical analysis. Weibull distribution is being used to model the probability of failure of the composite when it is subjected to a certain load. In this test, two-parameter Weibull distribution was used to study the cumulative probability density function. The Weibull distribution is given as below. Equation 3 shows the cumulative probability density function, or also known as the cumulative failure probability, which is F is equals to 1 minus exponential of negative tensile strength divided by scale parameter to the power of shape parameter or Weibull modulus. This function is then further derived by multiplying with natural log on both sides, which results in equation 4, which is ln times ln 1 divided by 1 minus f is equals to Weibull modulus times ln strength minus Weibull modulus times ln scale parameter. The f value can be calculated by present sample number minus 0.3 divided by total number of samples plus 0.4, which shown in equation 5. Next coming slides will be the results and discussion. The results will be analyzed on three bases, which are moisture uptake analysis, tensile properties analysis as in the tensile strength, tensile modulus, and strain at failure, and lastly Weibull statistical analysis. The first analysis is the moisture uptake. The moisture uptake percentage, or also known as the weight gain percentage, were calculated using equation 1. This graph shows the weight gain percentage versus time of all the samples. From the graph, it is found that the weight gain percentage of all the samples increase as the immersion time increase, and the average rate of water uptake of all samples is 5.2%. The evaluation of the water absorption profiles as a function of square root of immersion time in hours is shown in this graph. In all samples, an initial linear relationship between water uptake and square root of time is observed, as it indicates a typical Fickian behavior. From this graph, the rate of diffusion is calculated using equation 2. Hence, it is found that the value of diffusion rate after being immersed in distilled water for up to 30 days is 0.0027 mm square per second. Moving on to the next analysis, which is tensile analysis. This graph shows the stress versus strain curve of aged and non-aged specimens. From the graph, the initial strength showed by non-aged specimen is higher at 26.32 megapascal and reduced to 14.76 megapascal. This is due to the effect of the moisture exposure. Meanwhile, figure 3b shows that the initial tensile modulus has also degraded from 1.6 gigapascal to 0.78 gigapascal. Besides that, the water aging also has increased the strain at failure of the composite from 1.59% to 1.88%. This results suggesting that the composite become more ductile, possibly due to the effect of the plasticizing. Lastly is the Weibull statistical analysis. This graph shows the Weibull plots of the aged and non-aged specimen. From this graph, it is shown that the shape parameter or Weibull modulus of unaged is higher, which is 42.4, than the aged, which is 4.18, whereas the scale parameter of aged is 16.23 and non-aged is 26.62. Besides that, the R-square values from the graph of unaged resulting a higher value of 93% compared to the aged, which is 81.77%. Hence, these values show a good agreement with the experimental mean tensile strength value. Therefore, it can be said that the unaged shows higher reliability compared to the aged. Lastly, the cumulative density function describes the probability of failure of the samples. From the graph, it is found that when the aged specimen is subjected to a tension stress of 12.5 megapascal, then the probability for the specimen to fail is 0.28 or 28%. And when the stress is increased to 18.5 megapascal, the probability for it to fail has now increased to 0.81 or 81%. In a nutshell, there are three conclusions that can be made from all this analysis. Firstly, the exposure of the composite to moisture has reduced the initial tensile strength from 26.32 megapascal to 14.76 megapascal and tensile modulus from 1.67 gigapascal to 0.78 gigapascal. This is probably due to the continuous water immersion that causes a degradation of the fiber matrix bond, and when it is subjected to a certain amount of load, it tends to fracture and break. Therefore, non-aged specimen can withstand higher stress before it begins to fracture and break compared to the aged specimen. Moreover, the strain at break has increased from 1.59% to 1.88% after moisture exposure, suggesting that the composite become more ductile, possibly due to the effect of the plasticizing of the wood fiber and PP matrix. And finally, the Weibull modulus of the aged specimen is lower than the non-aged specimen, which is 4.18 for aged and 42.4 for non-aged. These values show a good agreement with the experimental results where non-aged specimen has higher reliability compared to aged specimen. Therefore, it can be concluded that Weibull statistical analysis allowing us to eliminate further experiments to determine the probability of failure of WPC. That is all from me. Thank you so much for the time and attention.